Hello everyone, welcome to the channel. In this video lecture, we shall continue with our discussion of the chapter Solutions. In the previous lesson, we have learned about the vapor pressure of liquid solutions, and we have also learned about the Raoult's law for solutions containing volatile solutes. In this video lecture, we shall first understand the effect of adding a non-volatile solute on the vapor pressure of liquid solutions, and then we shall discuss Raoult's law for such solutions. Let us understand the effect of adding a non-volatile solute on the vapor pressure of a liquid solvent. In a pure liquid, the entire surface is occupied by molecules of the liquid. If a non-volatile solute is added to a solvent to give a solution, the vapor pressure of the solution is solely from the solvent alone. This vapor pressure of the solution at a given temperature is found to be lower than the vapor pressure of the pure solvent at the same temperature. This is because the fraction of the surface covered by the solvent molecules gets reduced, and as a result, the number of solvent molecules escaping the surface is correspondingly reduced. Thus, the vapor pressure is also reduced. Now, Raoult's law for a solution containing non-volatile solute can be stated as: the relative lowering of vapor pressure is equal to the mole fractions of the solute which is non-volatile. Now, mathematically, for a solution containing components A and B, the vapor pressure of the solution can be written as P is equal to PA plus PB. Now, assuming that B is the non-volatile solute, we can write the equation as P is equal to PA, or P is equal to P naught A into chi A. Now, in this case, we can substitute the value of chi A by 1 minus chi B, since the sum of the mole fractions of the components in the solution is unity. On doing so, we can derive the relation for the relative lowering of vapor pressure, which is equal to the mole fraction of the non-volatile solute. Now, let us understand how Raoult's law can be a special case of Henry's law. Now, according to Raoult's law, for any volatile component of the solution, PA, or the partial pressure of A, is equal to chi A into P naught A, which can be rewritten as PA is equal to P naught A into chi A. That is, the vapor pressure of the volatile component, which can be the solute or the solvent, is directly proportional to the mole fraction of that component in the solution. Now, if the gas is the solute and the liquid is the solvent, then according to Henry's law, PA is equal to KH into chi A. That is, the partial pressure of the volatile component, that is the gas, is directly proportional to the mole fraction of that component in the solution. Thus, Raoult's law and Henry's law becomes identical, except that their proportionality constants are different, being equal to P naught A for Raoult's law and KH for Henry's law. Thus, Raoult's law can be a special case of Henry's law when P0A is equal to KH. It should be noted here that Henry's law is sometimes obeyed even by liquid solutions, and it is also observed that if the solute obeys Henry's law, the solvent obeys Raoult's law. On the basis of Raoult's law, liquid-liquid solutions can also be classified into ideal and non-ideal solutions. An ideal solution is that solution in which each component obeys Raoult's law under all conditions of temperatures and concentrations. An ideal solution may also be defined as that solution in which no volume change and no enthalpy change takes place on mixing the solute and the solvent in any proportion. At a molecular level, ideal behavior of solutions can be explained by considering two components A and B. In the pure components, the intermolecular attractive interactions will be of types AA and BB, whereas in the binary solutions, in addition of these two interactions, AB type of interactions will also be present. If the intermolecular attractive forces between AA and BB are nearly equal to those between AB, this leads to the formation of an ideal solution. A non-ideal solution is one which does not obey Raoult's law. For such solutions, the enthalpy of mixing is not zero, and the change in volume while mixing is also not equal to zero. A non-ideal solution can show either positive deviation from Raoult's law or negative deviation from Raoult's law. The deviation will be called positive when the partial pressure of each component and the resultant total pressure are greater than expected on the basis of Raoult's law. In such cases, the intermolecular forces between the solvent and solute molecules are weaker than the solvent-solvent and solute-solute molecules. This means that the molecules of A and B will escape more easily from the surface of the solution. The boiling points of such solutions are relatively lower as compared to those of pure components, because higher the vapor pressure, lowering is the boiling point. Now, by varying the composition of A and B in the solution, we see that at a particular concentration, we observe that the vapor pressure is maximum. Here, when we have maximum vapor pressure, that means the boiling point will be minimum. And here, the boiling point of this solution at this particular concentration will be lower than the boiling points of the components of the pure components A and B. Now, another point to be noted here is that at this particular concentration of the solution, the solution will boil at a constant temperature. Now, what that means is that here, if we boil the solution at this concentration, the solute and both the solute and the solvent molecules will evaporate at the same temperature. That means that in this case, the composition of the vapor phase and the liquid phase will be the same, or in other words, the solution at this concentration will behave as a pure solvent. So this type of mixture that boils at the constant temperature is also called as an azeotrope. Now, in this case, remember that azeotropes are
are constant boiling mixtures that when we distill they will have the same composition at in the vapor phase as well as in the liquid phase. Now in this case, because the vapor pressure is maximum, here the boiling point will be minimum, and hence these are also known as minimum boiling azeotropes. So we have to remember that solutions that have positive deviation from Raoult's law will give us minimum boiling azeotropes.
The deviation will be called negative when the partial pressure of each component and the resultant total pressure are lesser than expected on the basis of Raoult's law. Now, in this type of deviation, solutions will have a greater force of attraction between the solute and the solvent, and due to this there is a decrease in the escaping tendency of the molecules A and B from the surface of the solution, and as a result the vapor pressure will be lower.
Now again, if we vary the concentration of components A and B in the solution, if we vary the concentration, we observe that at this particular concentration of the solution, the vapor pressure is the minimum. Now, when the vapor pressure is minimum, that means the boiling point will be maximum. And in this case, what this means is that the solution will have a higher boiling point than the pure components A and B. Now we also have to remember that at this particular concentration, the solution will boil at a constant temperature. Now these are what we called as azeotropes. Now azeotropes are those mixtures that distill or that distilled at the same or at a constant temperature. Now what that means is that, as we have learned earlier, that means the composition of the solute and the solvent molecules will be the same in the vapor phase as well as in the liquid phase, or in other words, it is at this concentration that the solution will behave as a pure solvent. And here because in this case the vapor pressure is minimum at this concentration, so that means the boiling point will be maximum. So here we have the formation of maximum boiling azeotropes. So remember that solutions that show negative deviation from Raoult's law will give us maximum boiling azeotropes.